Welcome to Rambus Design Summit. My name is Frank Ferro. I'm the Senior Director of Product Management at Rambus. I'm responsible for our physical layer IP that includes memory and SerDes. Today, we're going to be talking about GDDR6 and how that memory enables high-performance inferencing in the AI market. I just want to let you know if you have questions, there'll be a pop-up and you can ask those questions in the pop-up and we'll do our best to get you answers as quickly as we can. So as many of you know, right now, the volume of data is just continuing to stress the infrastructure. And as we go through various phases of hardware, you can see that right now we have the current infrastructure is being stressed to the point where we needed more processing elements. And so the compute industry has done a really good job of increasing the amount of compute power. And so as that compute power goes up, which is a good thing, we also see the kind of negative effect is that you can't keep up with all that compute power. And so on the memory side, and we're starting to see bottlenecks emerge. And this is a cycle that goes through the industry where we see you have a lot of compute and then memory bandwidth, or now you have too much memory bandwidth and not enough compute. So now we're in a cycle where we've got a lot of processing power, but we need to look at the memory bandwidth. And so there are a large number of applications that are being enabled, by AI ML, including 5G and different cloud computing accelerators, and even at the endpoints with ADAS. And all of these have a common theme. They just need more data. So if you look at the existing architectures today, they're being solved primarily by your traditional CPU and GPUs, and they're doing a good job. And as you obviously everything's working, so that's good. But as the data continues to stress these systems, we see custom processors being developed that are very specialized for a specific neural network. And so what that does is it really helps from an overall performance. It improves the power and continues to drive up the overall system performance. And so Rambus is working with these companies doing these custom processors and helping them to find the right memory solution for those specific neural networks that they're trying to implement. So if we look at the requirements for memory across the internet, and you can see, I'm going to start on the cloud on the left side. So traditionally, most of the computing is done in the cloud. So we have what we call AI training, where neural networks are trained, and training means let's try to recognize what task that network's going to do. And so that takes lots of data. So the more data you pump into that network, the more accurate is going to be your ability to recognize the type of data that you're looking for. And so this requires very high bandwidth. And some of these networks can take a week or longer to train. And so you need memory systems with greater than terabytes of performance. And traditionally, a lot of the training is done in the cloud. So you push the data up into the cloud and train it, and then eventually those networks get pushed out to the edge and onto the endpoints. However, as we see as the data is growing, that you can see that's kind of an inefficient way to do things, right? That the more processing we can do, say at an endpoint or at the edge of the network, that's going to help the overall system, because we don't have to constantly be moving data, training, and pushing back. So if we look at the requirements around the edge of the network, specifically if we look at 5G, we're seeing now systems that are doing both training and inference. And so the amount of bandwidth is going up at the edge. So we call that kind of inline computing, where we're actually just doing the computing right there at the edge. And these systems typically are taking 300 to 500 megabytes per second of processing power. And again, if you look at the current systems at the edge and the current memory systems, they really can't handle that type of bandwidth. And we'll talk about that and look at that a little bit more later. And then also we'll look at the endpoints of the network as well. And again, similarly, the endpoints is where you're going to be very power sensitive. You're going to be very cost sensitive. So you're going to want to do the least amount of processing possible. And those systems are typically 50 to 100 megabytes per second at the endpoint. But again, the more processing you can do at the endpoint, the less you have to move the data up through the network or the edge. And so we're going to look at how we can do more of these processing at the edges and at the endpoints of the network. So you can see the amount of applications for edge computing is just exploding, whether you're doing image recognition or voice recognitions that some of us are probably more familiar with, but even very specialized applications for medical or weather, or even storage and database searches. So again, there's just an explosion of applications that are happening at the edge of the network. And if you look at the bottom right chart, you can see that the training is still dominant in the data center. So that data center is where you're going to want to do training, but you can also see that inference is growing as well. So once these networks are trained, you can run those, infer what those networks are going to be. But if you look at the overall amount of chips in the market, so clearly just looking at the volume of applications, we're up at the top right now. So you can see there's a large number of semiconductor AI chipsets for the edge market. So the edge is certainly, from an overall volume standpoint, you have much more of an edge infrastructure and going to require more and more chips. So what are some of the advantages of edge computing? I talked a little bit about this already, but we can zoom in just a bit more. So the less you have to move data, you're going to clearly reduce your latency and improve throughput. And also another big benefit of minimizing your data movement through the network is the ability to save power. So power has become, if you look at the amount of power that's being drawn, whether you're at an edge or a data center, power is a concern for everyone now. It's not just for mobile devices anymore. And security, of course, is another concern. The less you're moving data, the more opportunities as you move data, more opportunities for it to be breached. And of course, you don't have to, by not moving data, you take the pressure up the long haul links. And again, I'm not talking about SerDes today, but if you look at those links and the amount of bandwidth those links require just continues to grow. So that anything to do to reduce the pressure on those links is very helpful. And then as I talked about, as you train things up in the data center, then you can push those models out to the edge in the more traditional way. So now let's talk about some of the specific memory systems that are out there that you can choose from when you're building these different AI systems. So as I mentioned, AI training requires some of the highest bandwidth, and the highest bandwidth memory we have today right now is called high bandwidth memory, or HBM. And so the HBM, whether you're talking about HBM or we're going to look at DDR or GDDR. These are all basically the same DRAM technology. They're built on the same DRAM technology, but they're configured in a different way. So just to take a second here, if we look at HBM, you can see it's a DRAM, a typical DRAM, but it's configured in a 3D configuration. So the picture here on the top right, we have stacks of DRAM in a 3D configuration, and they're connected via these through silicon vias, and then that's on a layer that goes into the interposer. So you can stack the DRAM, and by stacking the DRAM, you're going very wide. You take the same DDR memory and now go 1,024-bit interfaces, say, versus a 72-bit interface. So that's how HBM does it. But with HBM then comes this 3D, with the 3D stack, you've now got to figure out a way to run all those 1,000 signals through, and that's where the silicon interposer comes in, or an interposer, and this typically silicon's used right now today, and that all sits in a package. So that's what we're calling this. There's a 3D memories, and then the packaging is a 2.5D technology. So this gives you very high bandwidth, but there's also, as you could probably already imagine, there's a cost associated with building such a sophisticated system around your SoC. But you've also have AI inference, again, as I talked about, the bandwidth drops. So now you can start looking at memories that are a little lower in bandwidth, like GDDR6 or LPDDR, and that will save you some cost and complexity. And so we're going to spend some time talking about that. In the automotive market for these ADAS, again, DDR has been your traditional DRAM that's being used. Low power DDR is being used in automotive, and GDDR6, again, these give good bandwidths, and we're going to look at those. And then finally, GDDR stands for graphics memory. That was traditionally used as a graphics solution, and it's still being used for graphics. I shouldn't ignore that, but it's because it's such high bandwidth, it's being expanded out into applications beyond the graphics market. So this chart, it may look a little complicated, but it helps as we're talking with customers to look at the different trade-offs. And in this case, we're going to look at the trade-off between memory bandwidth and the memory density. So if you look at the chart along the bottom, we have bandwidth, and then we have along this side, we have memory capacity. And so, and what we have up in the chart here, again, sorry, it's a little bit busy. This basically shows you the different types of memory. It tells you the number of interface pins you need and the number of chips you're going to need. So this way you can kind of say, all right, here I've got a system that needs about 300 gigabytes of bandwidth. And then what do those solutions look like? And then you can kind of work your way backwards. And then in this case, you say, well, okay, 300, but then I've doubled that with GDDR, and then you can even more than double that again with HBM. So if we look, what has the highest bandwidth and gives you a very nice density, and that's HBM. And we see customers saying it, if you're doing AI training, this is clearly a way to go. So HBM has become very popular, being used in different types of training applications. And then AI inference, again, if you look around the 500 gigabytes per second bandwidth, we have GDDR6, and then your traditional DDR is still being used in servers, and it's a very good solution for the server market. So again, if you look at the number of IOs here, so with HBM, you're going to get close to 1.8 gigabits per second. So again, very high bandwidth. GDDR gives you that nice trade-off, right? You don't need all this bandwidth, but you need more than you can get from DDR. And so GDDR sits in a very nice spot here for AI inference. I borrowed this chart from one of our customers, Acronix, and this is back a couple of years ago now. This is 2018, but what they were trying to show, the previous chart showed density versus bandwidth. Now they're basically showing the cost, and as I mentioned earlier, that HBM does have a cost associated with it. So they're showing the volume. So clearly DDR is the highest volume memories on the market, GDDR, and HBM even today, although this is a couple of years old, is still the lower volume. But then the price per gigabit, right? So if you have a data center application and you need all that bandwidth, then you're going to pay HBM. And if you don't need it, DDR, and then GDDR sits right in the middle. So again, this is another way to look at it. If from a cost standpoint, GDDR is a good solution. So let's look at some of these the system requirements for these inference cards. So I picked a couple. These are available on the internet. And so if you look at the different performance we talked about, this speed range of 200 to 500 gigabytes per second. And one of the cards that I looked at was a Tesla card from NVIDIA. And this card gives you 320 gigabytes per second. It uses 8 GDDR6s that are only running at 10 gigabits per second. So it's a 75-watt card. It was a very good solution for this particular inference card. Another card that's on the market is from a company called Acronix. This is a vector path card. Similar, they have a more bandwidth. They have 512 gigabytes of bandwidth on this particular card. And so this one can be used for both training and AI inference. And then another example is, again, this is off the internet. This is the opening up what's inside of a Tesla. And this shows the Tesla processors. And this is another system that's using AI inference. And we're going to look at that a little more closely. So if we look at two cards on the market that are used for AI inference, and now we're going to drill down some more. So these are similar types of card. This is a company called Inflame, and I already mentioned the Acronix vector path card in the previous. So if you look at the Inflame card, it's actually doing AI inference, but it's using HBM. So in this case, you're using HBM2 at 512 gigabytes per second with a 16 gigabit capacity. Acronix solved the same problem only using GDDR. In their case, it's similar processor, a little bit more performance, but now they've got 8 GDDR6s, exact same memory bandwidth, and exact same capacity. So this is a good example of trying to solve the same problem. One customer went the HBM route and got their inference card, and Acronix went the GDDR route. Again, two different ways. So you can see that at some points, you can go in either direction depending on your needs. So let's open up that Acronix card and look at their Speedster 7 architecture. So you can see they have 8 GDDR6s in the card. You can see along this side they've got 4 on this side of the board, on the chip, excuse me, 4 on this side of the chip. And so they've got these SerDes, pumping the data in, whether PCIe or high-speed SerDes, bringing the data in. You've got this 4 terabits of processing with the GDDRs, and you can move the data in and out. So this was one of the only FPGAs that has GDDR6 memory, and this gives them the performance they want without having to go the HBM route. I mentioned we'll look a little more closely at the Tesla inside of the Tesla. So this board, you can see they have 4 LPDDRs on the card. So this is their neural network processor. And these 4 LPDDRs give them 68 gigabytes per second of performance. And if you think about what could happen if they decided to replace those 4 with a GDDR, you could take 2 GDDRs, and basically you could double that memory bandwidth from 68 to 128 with half the number of chips. So you're going to save area on your board. The other advantage of using it is you can, with having more processing power, you can also get more automation support. If you look at this chart down at the bottom here, this is a chart I used for Micron, and basically it shows the different levels of as you're going autonomous driving, you have different levels defined, right? Where the highest level is basically the car driving itself, and the lower levels is where you're getting some assist from the car. So if you look at as you go up into the 128 gigabytes per second, now we're in the kind of the level 3 automation, where you can get more features basically in the car with less memory bandwidth switching over to GDDR. So again, LPDDR is good solutions working. Obviously, there's lots of Teslas out in the market, but if that same solution used GDDR, excuse me, then you could get more performance and even less board area. Okay, so now let's look a little more closely at the Rambus solution. So Rambus has been licensing GDDR6 IP for a long time. We were really the first commercial IP vendor to license GDDR, and it's a complete solution. So we have both the physical layer, the PHY, you can see here on the right, and we deliver PHYs as a hardened block, and we have a memory controller as well. And so it's a complete memory subsystem. And if you look at the controllers are very typically delivered, or they're very configurable. They're delivered as soft IP, and so you could these kind of lighter blue boxes here are configured by a customer. So we work with our customer to say, all right, what is your bandwidth requirement? what is your physical interface you need? Do you need AXI, or can you use a custom interface, a multi-port front end? Then we have different blocks you can customize. We have reorder cores, read, modify, write. If you need error correction, we have inline ECC. And so these kind of light blue boxes here, excuse me, are fairly configurable. And then we take that configuration and we validate that against the PHY, the physical layer, and then we deliver this as a complete subsystem. So, big advantage to our customers. You have a single point of support. We work with you to maximize the memory performance, to get the most efficient. And then we work with you on the physical design between the PHY and the memory. And we're going to look a little bit more at each of those. So let's look at the PHY side. So the PHY, as I mentioned, we have supports up to 16 gigabits per second, and all the way up to 18 gigabit per second PHY. And so these are hardened and time enclosed. And it's not just about the PHY. When you're doing these high-speed memory systems, you really need to have that complete system view. So Rambus provides not only the PHY, but we also provide the design support for the board, for the PCB, and the package. So again, it's a complete system solution. We'll every customer has different types of boards, different thicknesses, different types of materials you're going to use, and so we'll work with you to make sure we get that system right. Because if it doesn't, if we don't understand what the channel looks like, then you're never going to get your system to work. So we work in that very kind of co-design style and methodology. We support all the typical features you'd expect from the different DRAM configurations and densities. We also support what's called a clamshell mode. This is a mode in the PHY that allows you to basically double the density of your DRAM. So if you remember that chart way back where we showed kind of density versus performance, the GDDR spec allows you to double the density of the DRAM if you need more memory capability. And again, we support all the different training modes and calibration. Again, we work with the customer to bring up those boards and in terms of getting the system up and running and training. And we have a really nice tool called LabStation that we work with you to do that training. Excuse me. So as I mentioned, signal integrity is a key piece of the design. And this is again a talk that we did with our partners, Micron, DRAM provider. And you can see that with just a little bit of care in your design, you can get much better signal integrity. So you've got all these attributes on the left-hand side here that you have to consider, all these SI effects, right? Whether you have, return loss, crosstalk, different kinds of power supply noises. And so these are all things you have to think about when you're designing a system that's running at 16 gig or higher. And so this example actually shows we're doing things like back drilling and stubs. Getting rid of these stubs has a big impact, where you can see that your eye is closed and your data is failing. And with a back drilling and a one-tap DFE now, that eye starts to open up. So again, very careful design on the PCB, and Rambus has a lot of experience. And one of this picture here in the middle is one of the boards. We have two different development boards with different types of materials, and we offer those as reference designs to our customers. So now we look a little bit closer at the memory controller. As I mentioned, it's highly configurable. And that's because every application's a little bit different. And so we want to make sure that the key thing you want to be concerned about the controller is really optimizing in terms of your memory efficiency, right? You want to have very high DRAM efficiencies. And so we work closely with you. We have a very nice memory controller test bench that we provide with different memory models. And you can go through run your simulations, and then we'll work with you on those simulations to look at the different data you're running, and then how to optimize that data. And so you can see also the controller runs at pretty good speed at over a gig on the for an 18 gig operation, and then we will work with you on that timing closure. So we do the timing closure even all the way up to a gig. In a traditional DRAM system, what you normally do if you need ECC is what you have is called out-of-band ECC, where you have a number of DDRs, and then you'll have a separate DDR being used for error correction. Well, unfortunately, in GDDR systems, you can't do that because we're like, if you recall the picture where you only have one or two GDDRs in the system, so it would be pretty expensive to have a separate GDDR just for ECC. So what we provide is a inline ECC where we actually use some of the existing data to run error correction. And you can see the, we take a little bit of the bandwidth, maybe 10% of the bandwidth, but it's a much more efficient way to do error correction. So I can start to summarize here a bit. If you really look at the overall advantages that Rambus offers, is that we have the highest performance GDDR on the market. 18 gigabits per second we released back in 2020, and the 16 gig back in 2019. And this was built on a long history of high performance memory. Even before GDDR6 came out, Rambus had in-house a 13 gig device running back in 2010, and then even GDDR5. So we have a long, we're known as an SI company, and we have a lot of work that's gone into these systems. So a lot of experience. We've had great customer success. We've had designs across different markets, automotive, AI, and networking segments. And like I said, the key thing about Rambus is we work a little bit different than some of the other companies. We work very closely. You get access to our experts, and we work in a co-design methodology. So again, SI, PI is what we do, and we want to make sure that your system's going to perform at the highest level. So again, understanding your channel, working with our experts directly when we sign a contracts with you. So before I close, I just want to remind everyone that Rambus has a full portfolio of IP solutions. So on the right-hand side, you can see we not only offer GDDR, we also have high bandwidth memory, and there's also a talk I gave on HBM. So if you're interested in that, please tune into that talk. And we also have DDR and LPDDR, again, both the PHY and the controller. On the SerDes side, we have a complete suite of SerDes solutions for PCIe and CXL. We have Ethernet SerDes. We have SerDes to support the 5G market, ZIPRI, and we also have MIPI controllers as well. So again, full portfolio of IP solutions. So again, in summary, we have, again, AI is continuing to push the performance of systems beyond their current capabilities in terms of processing and memory bandwidth and efficiency. So we're looking at new architectures, especially around the AI inference and custom ASICs. And so working with customers specifically, at the different AI, whether it's edge or endpoints, on how GDDR6 can improve their system performance over what they have for DDR, and give them the kind of bandwidth that they're looking for. Again, Rambus has a strong experience in these very high performance systems. Again, 16 gig, 18 gig is not simple to design. So you need a company who has that deep history of SI and PI experience. And along with that, we provide the full solution, including the PHY and the controller. So I want to thank you for taking the time to listen to my talk. Again, I want to remind you that you can ask questions through the pop-up, and we look forward to answering those. And thank you for taking the time.